requests. Alright, so last time we were drawing ray diagrams and just dealing with spherical mirrors because they're easier. So I'm going to make this one a little bigger. So we have the center here. Okay, so it's called the principal axis. It's the center of the mirror. The focal point is right in the middle, so like midway between the center and the mirror along the principal axis. And what we could do with ray diagrams is we could draw an object, and the object exists at a certain location. Like if we move the object, we'll get a different result. And let's actually do that again, at least partially. Let's draw this first special ray, where we start out parallel to the principal axis and then go through the focal point. So that's one special ray that we can draw. Second one would be going through the focal point, and yeah, let's do that as well. We'll just draw two. And then it comes back parallel to the principal axis. So we get our image here. And using these diagrams, if we did everything very accurately, so I mean drawing like a nice circle here, and all these lines are parallel, and this would really tell us everything we need to know. Like the object distance is from the mirror to the object. And the height of the object is just here. And we call this di, the image distance. And I don't want to write it on there because it's too small, but just the, that would be hi, the height of the image. So basically, given the object, we want to know everything about the image. Like where does it occur? And how is it distorted by the mirror? Like here we can see it's inverted and it's also shrunk. But we want a precise way to do this that doesn't involve drawing accurate pictures. So these pictures are very useful, but we want an equation. And so we're going to derive an equation. But what I want to do is I want to draw another ray. Not one of the three that we normally draw. So I'm going to want to get rid of this one in the middle. We know where our image is, so we use this to get our image. Let's get rid of this just to kind of unclutter the picture a little bit. But we know this is where our image has to be. Right here. So I'm going to draw a ray that hits where the principal axis crosses the mirror. And then from symmetry, angle of incidence equals angle of refraction. The normal, or the tangent, at that point, would be perpendicular to the normal. So these two angles have to be equal to each other. And what I want to do now is highlight two of these triangles. Let's start with this triangle here. We'll do that in blue. And this angle is theta. We can say tangent of theta is HO over DO. So tangent is opposite, which is the height of the object, over the adjacent, which is from here to here. That's the distance to the object, that is DO. But we have another triangle here, which I'll draw in red, where again, this angle is also theta. So we can say tangent of theta is HI over DI. And this is actually not correct. I'm going to fix it in a minute. But, well, it's correct depending on how we're defining things. If we're just looking at this triangle, if HI is just the height of this triangle, like the magnitude of that, yeah, that's what the opposite this angle is HI, and from here to here is DI. However, we want to take into effect that this arrow is upside down. The image is inverted with respect to the object. So we're going to define HI in that case to be negative. So we have to write it like this. So tangent of theta is HO over DO. It's also minus HI over DI. Now there's one more thing I'm going to define. I'll do it over here where we collect our formulas. You're going to find magnification to be the height of the image divided by the height of the object, which is kind of just the obvious way that you would define it. Like if I told you the image was 4 centimeters and the object was 2 centimeters, you know, how much did you magnify it? You'd say by a factor of 2. The image is twice as big as the object. So like HI over HO is just 2, just a pure number, no units. So that's how we define the magnitude. And if we set these equal to each other, we have HO over DO equals minus HI over DI. So if we solve this, we want HI over HO. That'd be minus DI over DO. So we can combine that and just put it over here. So this is the magnification equation. So we define magnification. We also see a relation between the heights of the object and the image and the distances of the object and the image. So that was just from looking at these two triangles. Okay, now I want to draw another picture, and I'm not going to try and draw over this because I think I'm just going to erase the screen and start over at this point. So let's get rid of this. You redraw this spherical mirror. So say here's our object. Put that F on top. Now I don't want to clutter it up, so let's look at the second line. If we just went through the center, let's say the image is here. So we've got that. So we're going to look at two triangles again. One of them is not really a triangle, but let's start with this. Say in red, we have this triangle here. Okay, so that's going to be our first triangle. And we'll call this angle theta. So let's look at this side of the triangle here. We know that this is the focal length. Going from the mirror to the focal point is a focal length. Let's say that this triangle, this side is x. And if we start at the mirror and go to the object that is DO, so DO would just be F plus X. Or X is DO minus F. And so we can say tangent of theta, that's opposite, which would be HI, divided by X, which is DO minus F. So one equation there. And now another triangle, although we have a little bit of curvature here, a very good approximation. We can say this is a triangle. And again, this angle is the same as this angle. Just because, you know, you have two lines crossing, So those two angles are equal to each other. And so what we have from this equation, or from that triangle, tangent of theta. Now again, this is minus hi. Because remember, these are parallel. So we have minus hi over f. So from looking at that triangle, that's what we get from there. And if we set these equal to each other, hopefully I have enough room here, we can say hi over do minus f equals minus hi over f. Sorry, this, looking back, this one, that was from the red triangle. Tangent of theta, that's ho, the height of the object, divided by x. So, okay, so that's what we have. So, this is the height of the object. Sorry, I just wrote down the wrong thing. Okay, so what we want to do now is let's write this as hi minus hi over ho. So we bring this term over here, that would be equal to f divided by do minus f. Yeah, if we move this term over here and this term over here, we get this. And hi over ho, or minus hi over ho, is di over do. And I'm going to break this into two pieces. Well, not yet. Let's just do this for now. Okay, so we replace minus hi over ho. We just put the minus sign over here. That's di over do. And so what we have is a relation between di, do, and f. So in this first equation, we have something that relates the heights of the objects and the images. And then we have an equation that just relates the distances between the objects and the image for a given mirror. So like f is a property of the mirror, so we assume f is known, and then if we know di, we can find do, or if we know do, we can find di. Problem is, this isn't the most convenient form for that equation. So we want to fix this up a little bit. I want to flip it around, just so it'll be easier to work with. Let's say do over di. So we can just invert each side. There'd be do minus f over f, which we can then break into two pieces. Let's do it like this. Okay, so yeah, we flip it over. So do over di. Here we have do over f minus f over f. And now the last step here, let's multiply both sides by 1 over do. So that cancels out the one, well, okay, second to last step. What we have on the left side is 1 over di. And here we have 1 over f minus 1 over do. And so, well, it's actually the last step. Let's just move this term over to the other side and collect everything. So what we have is 1 over do plus 1 over di equals 1 over f, and that is the spherical mirror equation. So it took, we get this from these ray diagrams, and it takes a fair amount of algebra, but that is the result. Now, there's one problem with this, in that we derive this equation by looking at this particular situation here, where we have a concave mirror because the object's over here, the mirror's curving towards the object. What if we had a convex mirror? Should we expect this equation to work? No, we shouldn't. It would be a totally different situation. And so we could derive an equation for a convex mirror, but it turns out we like just having one equation. So I'm going to double check this on Canvas and make sure, but we should have a sign convention for lenses and for mirrors on, like, attached to the equation sheet. Where, actually, let's see if I have the notes. Yeah, so we have the sign convention, which means we can consider different cases, like different types of mirrors and so on, where we can just use this equation for any spherical mirror. So just like a couple examples. Here we have, like, focal length is positive for a concave mirror, negative for a convex mirror. So if we did this, if we wanted a new equation for a convex mirror, you know, we'd end up with a minus f or something. So it looks similar, except we'd have that minus sign there. But it's easier to just have one equation, and then we have a sign convention that makes that equation work for all these different cases. And then there's something about object distance. Now this one's a little curious. It says DO is positive if the object is in front of the mirror, and DO is negative if the object is behind the mirror, and then in parentheses it says virtual object. Now, what would that mean? Why would the object be, you know, behind the mirror? That doesn't make sense. And it's something we're not going to deal with for mirrors, but we'll come back to it when we talk about lenses. But the idea is we're looking at a single mirror. Like, what if we placed a second mirror? And so we're looking at this combination where the image we see is reflected off both of these mirrors. The way we would handle that in principle is we would use, so this is the object itself. And this creates a real image in this case. So we have a real image here. Although it doesn't always have to be real. But, like, say we used this, say we were looking at this image in another mirror. So this would be treated as the object for the second mirror. And again, we're not going to actually do any problems like that when we talk about mirrors, but we will do that when it comes to lenses. We'll talk about what happens if we have two lenses and, you know, use the image of the object to be the object for the second lens. So that's why DO can be negative, because the object for the second mirror, in this case, could be a virtual image created by the first mirror. But, yeah, so... Okay, and then let's go to image distance. It says DI is positive if the object is in front of the mirror, which means a real image. So here, we're getting a real image here. The image is in front of the mirror. Now, this is behind the mirror over here. And so, if, like, say we use this equation, and DI turned out to be negative, then we would know it was a virtual image. So let me give you an example of that. We'll just use a ray diagram. And yeah, circle is doing pretty good until the end. Okay, let's see if we put, I think this one will work. So yeah, ray 1 parallel the principal axis through the focal point. Ray 2 goes away from the focal point, bounces back parallel the principal axis. Okay. So if we did this, like, let's say in this case, let's say this is 2 inches. So DO is 2 inches. And the focal length, say, is 4 inches. Yeah, why don't we actually do this? Let's figure out DI. Now, this is something that occurs fairly commonly where again, we have DO and F, so it's not too hard to solve for DI. It's just the way the equation is written is kind of inconvenient because we have to find DI a lot. So let's solve for 1 over DI. That'd be 1 over F minus 1 over DO. So if we get a common denominator, should have left a little room there. Okay, so the common denominator is DO times F. We have 1 over DI. This would be DO minus F divided by DO times F. So we can even write this down as an equation because this turns up a lot. So DI would be DO times F divided by DO minus F. So you might even want to write that down on your equation sheet if you have a printed copy, just because it comes up fairly often. So if we plug in these numbers, we'd have DI is DO times DF, that's 8 inches squared, divided by DO minus F, so that would be minus 2 inches. And we get DI is minus 4 inches, which looks about right. Remember, the focal length is 4 inches. So minus 4, drawing's a little bit off, but not enough for me to worry about. And so again, we calculated DI and got a negative number. So if you look up image distance, it said DI is negative if the image is behind the mirror, and then in parentheses it says virtual image. So just by using the equation with the sign convention, we can tell this is a virtual image that's behind the mirror. So again, in problems like this, I highly recommend just doing a quick drawing, especially if these two things agree with each other. That's a good sign. But yeah, you can just use the equation, these two equations and the sign convention, and learn everything about these images. But it's always good to check if possible. Sometimes it's hard to draw this diagram to start with, because like if you don't know where the object is, then you can't really do much. But you can, once you find the object distance, then you can plug it in later and just check it. But if you don't know where the object is, you can't start with the diagram. But if you can, it doesn't take too long to just draw it. Okay, so yeah, I guess that'll be it for this one. So again, this equation works for spherical mirrors. If we use it with the sign convention, it always works for spherical mirrors. And yeah, so that'll be it for this one.